So I'll begin my presentation. The topic is the training variational quantum algorithm is NP-hard. And as it's written in parentheses, it's the part one costy. I'm supposed to just divide the topics in two sections. One is the binding exact solution is NP-hard, and the binding approximate solution is a apex. Apex hard, which is the some relatives of the original NP-hard classes. So which means that if you approximate some problem within to solve it in polynomial time, then must have some range of errors that can be just some kind of, there is some upper bounds for, which means that it's not that very exact. So I'll begin. So part one will be topics about this binding exact solution. So before we begin, let me start from this some preliminaries. So the topic is the first preliminaries is that about the variational quantum circuit, which is just the binding some expected value with the quantum circuit called ansatz, which has the parametrized quantum circuit. So when you studied about the quantum mechanics when you're undergrad, you may learn about the variational principles, which has the just test for the just let me call it template test function wave function. So test wave function, which actually in here is just a quantum circuit, which means that you keep changing the variables in the quantum circuit. So and perhaps you can just wish that balancing the optimal values for example, just minimizing the energy level of the Hamiltonian by just using the optimization algorithms in these quantum circuits in here and changing the parameters in. And the compressive theory is quite straightforward. I think we have learned it, and which means that there's kind of hierarchies between the algorithms, and some of them are only requires the polynomial, log scared space, or some of them may require the polynomial time for the solving the problem, or some of them might just cancel in polynomial time complexity. And what we are really interested in is the relations between the P and plus P and MP and MP complete and MP hard. So the P problem is the problems that can be solved in polynomial time, and the MP problems that can be doesn't have any proved result that it can be solved in polynomial time, or it is kind of non-deterministic solved in polynomial time, or just more rigorously speaking, it requires the polynomial time to verify it is right answer or not. And the problems that even harder is called MP hard, and the intersection of the MP and MP hard class is called the MP complete problem. So if someone succeeds to prove that MP complete can be solved in the polynomial time, that means the P equals MP satisfies. So that means we kind of, what I say, just get a good accomplishment in the compressive theories. So the goal is the current challenge of BQAs has we help the gradient vanishing problems when solving with the variational quantum circuit, which means the often called is names Paretos, and we'll show that there's kind of exists a persistent local minima can also list our problem that can be efficiently solving the problems is visible. So we're gonna use this famous NP-hard problem in here, which calls the next problem, and the first, yeah, we're gonna. I'm not sure I included that in this slide, but there it is so many local minimums in the some post function horizons. So that means that it is not really feasible solving solving the variational quantum algorithm in polynomial time. So steps of the proofs are the following. So first, just suppose we have oracle that returns the perfect solution without just for the quantum, how do I say? So quantum compute without we don't have suppose we don't have the quantum computer, but we have some corresponding oracle that perfectly returns the perfect answer. We just like we run the quantum computer. So we're gonna have that suppose that perfect oracle here, and we as any other variation of quantum algorithms, we're gonna solve the optimization with that oracle. As we're gonna show that even if we have the quantum computer corresponding oracle that is still NP hard, and we're gonna scale down the number of the systems. I mean these parameters written here, but it's kind of as type I think. So so we just squeeze the size of the system, and we're going to try to solve it, and that's still the NP hard, and we're going to, based on the second results, we're going to prove that the third some general variation quantum algorithms, which is useful for our purpose, like solving the VQE problems, like or just performing a problem within here. So it is still NP hard. So and there's some derivative terms in here, which means that actually there's another part of in this paper, there's another part of just proving that some, as I mentioned, some of the approximation algorithms still have its limitation that may not be very precise. But I'm going to skip it here because it's too. Frankly speaking, it was too hard to show in here, and I think I didn't understand some of them so perfectly. So those problems are NP hard. So let's start from the very beginning problem. So we know what is mixed curve, right? So suppose we have the adjacency matrix that has the only elements has 0 or 1, and each rows or columns corresponds to some nodes in graph. And it is, of course, since we're gonna consider the very simple problem, so we will consider the undirected graph problem. And so that is is following. So we're gonna find some subset that including some nodes in graph that maximize how do I say, the sum of the nodes between some of the weights. I mean, just let me show you the picture first. So we're gonna show that two groups. We're gonna find that the two groups that if we cut a group of nodes in a group of the edges in here, for example, we're gonna find that the answer is cutting these edges gives the maximum value of the cutted weights of the cut wedges. So basically, the finding the maximum value of the cutted notches and cutted edges is the NP hard, which is the famous because it already shown that this resatisfiability problem can be reduced into discrete mixed curve problem. So far, any questions?
Please explain the problem over time.
So we have adjacency matrix in here. So here's if you just match each columns just for nodes, just 1, 2, 3, 4, and adjacency matrix has is connected edges in here. and 1 is 2 is connected, so it has 1, and 1, 3 is connected 1, and such like that. So, and if we try to find some two groups that, so two groups of node that while just cutting the rate of edges to be maximized. So in this example, if you cut in just directly here, we're gonna just check 1, 2, 3, 4 has 4 weights, which is the straightforward. It has the biggest cutting weight in here, and also it still remains two groups are remaining without this forming group. So discrete mixed cut is obviously hard, and so based on this problem, so we're gonna also show that if we make it instead of the discrete problem, if we consider it as a continuous mixed cut problem, then it is also the NP-hard problem. So we're gonna first define our cost function as follows. So where did this cost function comes from is so this is the original discrete mixed cut problem, isn't it? And if we consider if we just match corresponds to if we define the parameter v in here, which corresponds to each node in graph, and we just assign the values the vi's or vj's to 1 or 2 minus 1, which means that if they have the different values, for example 1 and minus 1, they belongs to different groups. So in here, if the 1 and 1 is the same, and then means that that gives this difference, so it gives it's different, so that chronicle data becomes 1, and it's same if the chronicle data becomes 0. So if it's successfully just by partitioning two graphs into two subgraphs, and by just assigning 1 or minus 1 to vi or vj, and that also corresponds to some discrete problem. So by just rewriting this formula as follows, so which means that if it's same, it gives the 0, and or it's difference, it gives the -2. We somehow hope that this minimization problem also means just same to be the discrete mixed cut problem. So if we change the vi and vj in here to cosine pi I and cosine pi j, and our claim, or just this paper is claiming that the continuous mixed cut problem is still NP-hard. So why is it happening? So the continuous mixed cut problem is equivalent to the discrete mixed cut problem. So which means that if we suppose we have I'm not sure we have, so we have this original continuous mixed cut problem, and we will suppose that the cosine pi I here is we can fix the value of the cosine pi I to some specific value to cosine x, and just finding the only pi j to find some optimal values, just only optimizing pi j. And however, if you just let the only cosine pi j to optimize it, but the cosine x still has it has its impact on this cost function. That means that it only depends whether the pi I is 0 or pi I is pi, which means that whatever the pi j value, the parameter in here takes the takes its value for the while for the optimization problem, it must be just lower bounded by some part the value of the cosine x in here, which means that it so it can be only to be take its value whether it's 1 or -1, which means that it doesn't matter what pi j should take. What pi j takes its parameter value is just it depends on the pi I is 0 or pi I is pi. So the problem is again, so we just suppose this cosine I and cosine pi j is here, and without any some exponential time reduction or some kind of other reduction, we can easily see that the problem becomes the original discrete Mexican problem. So the problem is, as you can see, problem is reduced to iteratively choosing the pi I is 0 or pi I is equals pi in the some i's in the some subgroups of the D graphs in which called the here, and without including the original problem view. So the continuous problem is the discrete problem in polynomial time without reducing approximation power. So this is the proofs of the problem. So you might be confused about this kind of reduction problem. So just I'll give you some, I don't know. So from now, so we proved that the continuous Mexican problem is equivalent to a discrete Mexican problem. And we will use this continuous Mexican problem as a template of the problems that we're going to consider. So before I step forward, so I will just kind of give some preliminaries about how we can proving NP-hardness. So suppose we have some or a problem X that known that is NP-hard, and another problem Y can be satisfied can be polynomially reduced from the X to Y. Then the problem Y is NP-hard, which is the kind of you might hearing is of course it works, but the problem. So the point is here if we know there's some very hard problem in here, and there's some problems that we wonder is NP-hard or not. So we just enough to some of the inputs in here as the polynomial time corresponding functions can be defined that starts from the very hard problem, which is the NP-hard problem from the X to from the X. So we're gonna use this theorem for the following problem. So X will be Mexican problems and the Y is the objective problem. So the third problem is the VK minimization with the oracular problem. So this is the basically oracle remediate problems first. So we're gonna have some problem with instances that a set of generators that consists of Hamiltonian or Hermitian operators and the observer all acting on Hermitian, the Hilbert space of the C to the tensor product of n given in terms of the power basis representation. So which means that and we're going to have the oracular sets that can give you the answer of this problem that even we don't have any kind of quantum computers or other similar machines. Just is kind of tools that we want to make. For these steps, we don't want to consider the quantum computers. So just solving the problems, classically this problem is NP-hard is what these authors of the problem paper was to show here. So we're only focusing on the classical optimization algorithm as written here. And others claims that assuming the P is not equal to MP, there's no deterministic classical algorithm that solves problems 3 in polynomial time. So the conclusion is the problem 2 can be reduced. I mean, the problem 2 is the continuous Mexican problem can be reduced to problem 3 in polynomial time. So we're gonna first model its observability. So observable is the essay using Ising Hamiltonian encoding as follows, and we will how do I say, just define the unit rows as follows. So H is the just Pauli operators of the Y and acting on some qubits or systems in our Hilbert system, and the unitary can be defined as follows. And if we just put all the unitaries and unitaries or observables just in this problem and solving it directly reduces the problem to be cosine pi I times cosine pi j minus 1, which is just what continuous Mexican problem what we have solved. So you might just confuse what we are doing here. So we started from the Mexican problem, and we try to find that there exists function f in here that reduces the object problem. In here we have regular problem with some kind of the observables and unitaries we define here. You might wonder, hey, we still have that kind of the problems without having this kind of constraints, but in definition of the NPR problem, that it is only enough to proving that existing problems in NPR problems can be with all the inputs of the known and the problem that known as an NPR problem can be reduced to the problem, can be matched to the inputs of some parts of the Y. Objective problem is enough because the NP hardness is showing that it has kind of lower bound, or just to say upper bounds of its problem hardness, that it might have some difficulties that can be reduced into the really hard problem. In here, just it is NP hardness and the Mexican problem. I mean, it's just kind of matter of potencies that this problem can be really hard or not. So this was the problem 3, and having any questions so far?
Could you show the function of problem 3?
Problem? What is the problem?
3.
Here? Yeah, it's not quickly, but we just want to focus only for the classical parts, because we don't just suppose that there's a quantum circuit or just a quantum something in here. We only just want to some kind of mathematical templates. Yeah.
Yes.
So
then is there any probabilistic classical algorithm that can solve?
Yeah, that's another topic of this paper, and actually they already, as I mentioned, they already showed that there's probabilistic approximate algorithm, but it has a fixed error rates in here, so that can't be break. So that's another topic, and I just want to deal that, or I also want to deal that problem as a part 2 of this seminar in here, but I didn't have much time to prepare for that. So so far we define the problem 3 as by just making a graph and the problem setups as a just match to the each graph node, one node matches to the 1 qubits. So which means that if you have the 10, a graph has the 10 nodes, and that means that we have to prepare the 10 qubits in here, which is this, how do I say, is ordinary QUBO setups or QUBO action setups. But there might be someone say that, hey, I think that's too inefficient. Why don't we just scale down the original problem to the log? It has the log D, which is we want to just exploit the advantages of the quantum computing, or just quantum based computations. But so why don't we just reduce the system size and let this solve it? There might be some hardness can be dependent on the system size. So question is the really reduce the complexity of the problems, or the complexity of the problems really. And this is the problem. So only if the change is near, there's no more tensor product of the two. We just reduces the problem that only can covers the original problem with the log scaled number of qubits. Just for examples, recursively speaking is the system size, but I think it's more straightforward to just consider as a term of the qubits. And they still claim that the Vk optimization in here is the NP hard. So the conclusion is of course, the problem 2 can be reduced to problem 4 by manual reduction, which means they just polynomial time reduction. But how? So we first define some observable that has just 2 times bigger than the original problem for the problem's size, and which is divided as follows. And again, we're gonna redefine the observable O prime as to be O. We're gonna redefine the O by using the definition of the O prime here, and which is not straightforward, but you can imagine that it's kind of block diagram with the block diagram that the diagonal has some kind of X patterns, and the off diagonals have some different X patterns in it. And we're going to choose the initial states and the Hamiltonian generators as follows. And yeah, it's kind of straightforward. Because it's just by directly calculated, you can really get the parameterized state and expectation value as follows. So yeah, I actually formulated this problem, and I found that this still really works. So I will just skip the details in here. But as you can see that as we saw in the problem 3, so we define some observable here and the unitaries, and for that given the constraints, given such constraints, we showed that the problem can be reduced to the original continuous Mexican problem, which is the NP hard. So the problem O is NP hard is proved in here. So any questions so far? Okay. And as a corollary, the decision version of the problem O is NP complete, because we show the problem O is NP hard, and if we define this decision version, which means that the problem has some kind of criteria that we want to, whether the cost function satisfies or not, which means that we can just verify the given answer satisfies this kind of criteria or not. It's by only can be verified within a polynomial time, which is the definition of the empty class. So it's kind of correlated. And I don't think we don't need to explain this. Because it's too straightforward. And the problem, I will divide the problem by the year. So we're gonna divide the pre-Fermionic models that has just models the Fermionic many-body systems that does not have the practical particle interaction. Right? Not sure that this is the right description. But anyway, so and it's easy to model the system under the time evolution for the so-called Gaussian input states and Gaussian observable. And it's kind of a nothing but a formulation. So we will define the Gaussian Hamiltonian. So for the narration operators like C1, C2 to Cn, we will consider the Hamiltonian observables as follows. So we will call it the Gaussian Hamiltonians is it's just only formed with this annihilation and creation operators and its corresponding correlation matrix values, which is here Hij and the Gaussian observables is formulated with the sum of them, and the Gaussian state is Gaussian state is divided with these Hamiltonians and can be formulated very easily. And it's actually formulated in its supplementary, so I'm just gonna directly write it here. So Gaussian Hamiltonian is divided as follows, and the Gauss state of Hamiltonian H is divided as follows. And the proof is the omitted here, sorry. So it takes almost 2 or 3 pages of the proving this problem. This for supplementary, if I remember it correctly, and we don't have the space for them. And actually, I think I don't really understand this process here. So, and so we're gonna define the problem item here. So coefficient matrix and for the we will define the coefficient matrix for Hamiltonians, for Gaussian Hamiltonians, and its observables divides in the Hermitian of the space of has the C to the n, which is the same set of in the program 4, and the coefficient matrix divide the quadratic observables H0 and H1, and all by just defining divide as follows, and the initial set of initial states is defined as based on the very generous Hamiltonian of the setups in here. So evolved state would be can be denoted like follows, and we're gonna just try to minimize this expectation value of the given observable and the quantum states. So which is you might kind of familiar with this kind of Hamiltonian because this is the quadratically quantized version of the Hamiltonian, which is often dealt with the VQE problems, which means it has some sort of it is VQE problem does not have interaction between electrons and only considers the quantum states that were approximated by a thermal state of the Gaussian Hamiltonian. So problem is still empty hard even if the initial states law is still pure. So again, the problem 2 can be reduced to the problem 5, which is sort of the Mexican problem actually. So again, proving this is the kind of straightforward. So we're gonna first define the just correlation matrix of the Hamiltonian operators and that has some sort of constraints, right? For Jero's Hamiltonian correlation matrix, it has the X, but the ice Hamiltonian has how do I say, it's chronicle data of the original matrices, and we're gonna just put in a as one diagonal 1 - 1 matrices in here, which means that it wants to be has this only some part of the diagonal products has to its Hamiltonian values and others letting others to be zeros in here, and it only has the eigenvalues of the 1 - 1, 1 - 1, 1 - and so on. And the SA and for our for convenience, we're gonna define the gamma ij in here, which is defined as follows, and in supplementary they show that the sum of this big matrix gamma is actually has the sum of the I divided by 2D here. And we're gonna also define the observable correlation matrix of the observable O is the correlation matrix of the observable O is defined as follows. And so in here we already defined, if we just directly putting our definition in here, the formulation will be such like this, and this is actually a scalar or not just a matrix. So we can just apply the trace matrix trace operation only in here, and which is defined in here. We're gonna substitute the gamma ji in here, and this summing them all, actually gamma ji is already known to. Sorry, this is not a sum. It's the kind of big matrices with the paired with the one divided by 2D in here, and the sum applying sum in here is the returns to one divided by 2D here, and the observable O pi is defined. We're gonna use the same O correlation matrix definition in here as we define in problem 4 in here, and we already showed that if the observable has the form of this kind of formulation, and it can be it can be directly formulated into the problem of what we did in problem 4, which has at the end of the calculation it reduces into the Mexican problem, and this is the direct reduction of what we have shown in previous problem. So it becomes the post function of the Mexican problem, and it ends the proofs of the problem 5 is NPR problem. And so far, so we already show the oracular BQA optimization, oracular problem, and the scale down in the system size, and the presenting in the general BQA problem, and we showed that they are all NP-hard problem. Then what would be next? So we have covered the training BQA's NP-hard so far, but we need to also hold the approximated algorithm which had the polynomial time complexity. When said it can't fully approximate the original problem, and it has kind of limitation that has some fixed value of the error rates, and it is called the apex hard problem. Is the relatives of the NP hard, or this kind of NP hard problem, and which means that it basically has its own limitation, even if the algorithm solves the original problem in polynomial time complexity. So I will try to show it next time in seminar in here. So this is the end of showing finding exact problems, solution of the BQA problems are NP hard. And thank you for listening. Do you have any questions?
This is very light question. Is there any connection between the NP hardness of the optimizing BQA and the existence of variables?
So yeah, I'm sorry. So I didn't include the extensive. Yeah, technically speaking, it is not very related, but this problem show that the continuous in supplementary in this paper show that there's a lots of the stationary points in original continuous mixed problem, which means that they could just stay. They can be modeled just many numbers of the local minimas that exists around the optimal solution, and it is already shown in the supplementary. So in conclusion, it doesn't have the direct relation between parameters, but it it might just it makes the optimization process very hard.
This question may be not related to your topic, but it's my first time to see the continuous maximum problem. And it is well known that there's a exact mapping between the discrete Z2 maximum problem and some Ising. And it can be solved efficiently by some classical quantum algorithms like QA. And my question is there any mapping between the continuous maximum problem and some Hamiltonian slide? Bosonic Hamiltonian slide?
Sorry, I don't have a bunch of the Bosonic problems. So, but this problem, it is hard parts of this paper. They already covered about QA or A, and it's still a case hard problem. So next time, if I can be properly prepared for it, then I will not show it this and be how it is.
So, is it guaranteed that we will find the optimal solution? Is it guaranteed that we find the optimal solution?
So am I understanding right? So I mean, if it is a hard problem, there is no guarantee. You're asking about it. Is it not guaranteed to have optimal solution?
Well, is it guaranteed that you'll find even a final?
For some nodes, I think it can find, but basically solving it means that you're solving the problems that are most same with the finding the mixed problems or three satisfactory problems, which means just has the exponential tendency. So this is the end of my presentation. Thank you for listening.